So here are a few computation problems from the openstax textbook for Unit 4 on rotation, and that would be statics and torque, as well as rotational motion, which is also the dynamics of rotation. So I'm going to get to the second problem. That's the one I'm going to do here to begin with, but very quickly about when opening a door and so on. Here would be the original problem, and hinges and doorknobs. So I pulled this one up, and there's a reason why the doorknob, for example, here is toward the outside of the door so that you can maximize the lever arm, and therefore you can use the smallest force possible in order to apply the same torque around the hinges. And then also it's best to apply the force perpendicular to the doorknob. That can be shown in this one here. Yeah, you don't want to exert the force here at this angle here. You want to exert it over here, maximize the lever arm, and perpendicular, which also maximizes the torque then. All right, so I should start with problem 2, which is when tightening a bolt and so on. Let's see what it says here. When tightening a bolt, you push perpendicular on a wrench, just like it is with the doorknob, with a force of this much at a distance of this much from the center of the bolt. How much torque are you exerting in Newton meters? And all it is multiply the two numbers, convert this torque to foot-pounds. I put on the side here my own comments. Unfortunately, they don't turn up when you access the openstax textbook. So here they are. Pretty much torque equals force times lever arm several times over, and then yeah, certain things happen other times. Newton's second law, for example. Okay, for rotation in this case. All right, so this particular one here is just going to be multiply. Okay, so there we go. That looks like a... What did I do with that? I think this is shooting Nerf guns at an angle, and I come out with a speed of 18 meters per second from possibly my trigonometry class, maybe my physics lab. Anyway, so here's the bolt. So all it is 165 times 0.140 meters. Make sure that they are in base units so that you do come up, so they're both in Newton and meters. So you're going to come up with Newton meters. And I think the second part is convert this torque to foot-pounds. So Newton to pounds is divided by 4.44. That one comes, by the way, from dividing 2.205 from kilograms to pounds into gravity, 9.8. That's where the 4.44 conversion factor comes from. So newtons to pounds. And then, let me think about that, divide by 0.3048, which is how many feet are in a meter, or if you take the reciprocal, you have about 3.3 feet. 3.3 feet to the meter, and there we go. So that's 17.0 foot-pounds. And here we go. That would be a solution. That's a 23.1 Newton meters that I had a moment ago, and here's the 17.0 foot-pounds. Notice it's in the American system pretty much the same thing. Foot-pound, Newton meters, just a little bit turned around, but otherwise it's pretty much the same thing. Of course, there's a conversion factor. By the way, they use kind of slightly different conversion factor from mine, the 0.738, but if you look at the calculator, that's actually the same as multiplying 4.44 times the 0.3048. So I just use these conversion factors, but again, they're completely equivalent. All right, I'm going to take a break for the next problem. All right, the next problem I want to do is this one here with the seesaw. So I'm going to go over here, repeat the seesaw problem with center of mass of seesaw this much to the left of the pivot on the other side of the lighter child, and assuming mass of 12 32.0 kilograms for the seesaw. Yet other data in the example remain unchanged, explicitly show, and so on. So I'm going to click on this one, and that should get me to the example. So there it is. Let's see, CPROM 5. Okay, that's my thing here, seesaw, and so on. Whoa, quite a bit I put in here. So net torque equals 0. Oops. Clicked on that one, and then I came up with equilibrium of torques. Okay, there it is. And then here, most people have perfect intuition about seesaws, knowing that the lighter child must sit farther from the pivot, and that a heavier child can keep a lighter one off the ground indefinitely if they sit too far. So you can see that here. And then if the seesaw's mass is centered right on the pivot point, which by the way in this problem it's not, that's kind of what they try to point out. So, but if it is, then it's a simple ratio of the two masses versus the two lever arms, of course, in the other way around. So here we go. Seesaw torques on a seesaw. So they said keep all the other numbers the same here. So the lighter child, 26.0 kilograms, sits 1.6 meters from the pivot. The second child has a mass of 32.0 kilograms. How far is she from the pivot? Okay, now the thing is, what they say in this problem, I'm going to go back here, is that the seesaw is actually not centered. It says right here, with the center of mass of the seesaw 0.160 meters to the left of the pivot on the side of the lighter child. Okay, so we have to keep that in mind. So whoever designed that particular seesaw didn't pay that much attention to it. I'm going to go back to the example here and so on. By the way, at some point it said in the example here, seesaw of negligible mass. Even if it was centered, actually, it doesn't matter what the mass is. It balances itself no matter what. I mean, as long as the kids are okay there. But in this case, we do need the mass. We do need the 12 kilograms for that. And we also need to determine what the supporting force is. All right, so here they go into the algebra. And I could have written this myself, but here it already is from the solution. So mass on the left is, that's for the kid on the left, 26 kilograms. R1, this is the kid, 1.6 meters to the left. That's a whopping 5 feet. That's a 10-foot long seesaw. I guess they are. And by the way, that here in my book should be a negative because it points to the left. Okay. And then here the data for the heavier kid, and the unknown is the distance where the heavier kid sits. Then this one here is where the seesaw is, so that should be 12. It is 12.0 kilograms. And the seesaw's center of mass is actually to the left. Again, that should be a negative because it points to the left. I think they said that right. Yeah, to the left of the pivot. So first find this one. Okay, they're starting out with the first equilibrium condition, which is the torques must equal out to 0. And later on, they're going to go to the forces that have to be also come out to 0. Okay, before I get into the algebra here, let me go back. So let's see, here it is. So this kid over here produces a counterclockwise torque. This kid over here produces a clockwise torque. By definition, the counterclockwise torque, as it goes in this direction here, coming from the positive x-axis actually around, kind of the coordinate system that you find in math, that's the way the angle is measured, is actually positive. So a counterclockwise torque is considered positive. A clockwise torque is considered negative. And then the center of mass of the seesaw is actually over here, which means it's also producing a counterclockwise torque, also a positive. Now, remember a moment ago I said something about that the kid sits to the left, and so is the center of mass to the left, so both of these are negative. So keep that in mind. Each one of them is negative, and their weights are pointing down, which means that's negative as well. Well, multiply negative by negative, weight times the negative weight times the distance to the left, which is negative, and you come up with positive, which is very convenient because we do come up with a positive torque here, as it should be. This would get into multiplying vectors with each other, which I really want to leave out here, so it's kind of convenient that it comes out that way. So for the girl then, sitting on the right-hand side, that would be a positive distance, but the weight, of course, is still negative, so negative times a positive indeed is a negative torque, just like it should be. All right, then going back to the algebra here. So the net torque here, I would write it as follows. I would write the total net torque equals 0. And then we have the 3 torques that are listed over here, all on one side. 2 of them are actually positive. That's actually these 2 here. Remember I said these are counterclockwise torques. And this one, when you put it to the left side, that's actually negative on the left side, right? Meaning that it's a clockwise torque. And that equals 0 because the whole thing is balanced. No, that's what they say. They don't rotate crazy around, but the whole thing is balanced. Okay. So that's the way I would write it. As far as the algebra is concerned, that's actually the same, so we can start here. Oh, the other little thing I would do is I wouldn't write a smaller case W for weight. I would say capital F, little w for weight, so the force of weight. That's the way I would write it. But okay, either way. Then they are solving for R2, which is where the girl should sit. And then they plug in all the numbers. You can see that here. And yeah, if you do that, 26 times 1.6 is in the neighborhood of like somewhere around 40, a little bit less or more. This one is in the neighborhood of like 1.5, so not that much. And then you divide by 32. Yeah, if you put it in the calculator, you do come up with 1.36 meters. Compare the 1.36 meters to the 1.60. That's where the lighter kid is sitting, so that's obviously less of a lever arm. Well, the kid's weight is more, or mass is more, 32:26. But it's not a simple ratio as what I showed earlier, because the seesaw is included as well. The seesaw's, again, center of mass is not centered where the pivot point is. All right, so 1.36 meters here. Since the children are not moving, yeah, well, they weren't moving anyway for the torque as well, the net force is 0. See, this is where I would write the torques just the same. Net torque equals 0. And yes, then we have the support force from the pivot, so from the fulcrum, right, let's see if this right here, so the support force right here, Fn, F support, Fp, I guess, maybe for pressure. And then the weights are pulling all down, so both kids' weights are pulling down and the weight of the seesaw itself. So it's just a matter of adding these 3 weights, which is what they're doing here. So support force minus the 3 weights, because they're all negative pointing down, being weights, which means when you put them to the other side, of course, they all come out to be positive, which makes sense because the support force is supposed to be positive. So basically multiply each mass by gravity in order to get its weight, and you come up with 686 newtons, which I showed that earlier. I divide by 4.44. I come up with in the neighborhood of like 150 pounds as a support force. Okay, that took me a little bit longer, but this was an involved problem. They wanted to do 2 things, and there was algebra involved, and I wanted to explain a few things here. All right, again, a little break for me, and I'm glad I actually took that break earlier because I needed to prep this problem. All right, again, a little break for me. Again, I took a longer break in order to prep this problem. So it's actually a double problem here. Horse leans against the wall and then force on each foot. And here I already supply one of the answers. This first one here uses actually the torques. The second one's pretty much just about the forces here, this one. And here's the original problem from the book. So horse, one of this cowboy leans against the wall. And to me, I've watched this movie when I was a kid. It's Cat Ballou with Lee Marvin. And they should have mentioned this here. Turns out up on my recommendation, they actually put it in the second edition of this book. And then there is, as I said, a follow-up. So let's go here. And then I'm going to do this problem in just a moment. Here's the video, by the way. And then I forgot to actually mention, hey, here's just a normal seesaw video, right? So there we go. And that's how you would do it. And I guess, okay, that's not, so is it the mother is not sitting at the appropriate distance, so she actually has to control it, actually push down or lift up on her side in order to make sure that the kid is going down. All right, but the horse here. So it says that calculate the magnitude direction of the force in each foot on the horse in that figure, assuming the center of mass and so on, the total mass of the horse. What is the minimum coefficient of friction between the hoofs and the ground? Note that the force exerted by the wall is horizontal. So in the previous problem 6, it computed the force that the wall exerts on the horse to 1,430 newtons. That's what you see right here. So that means, where'd it go? Oh, there. So that means that the force here from the wall on the horse and back, it's Newton's third law, is 1,430 newtons. And it did that with the torques. Here, this is just about the forces, which means when the wall exerts a force in this direction of 1,430 newtons, then the friction here must actually balance that. And since 2 of the feet are on the ground, it's just half of that. So 715 newtons on each one. By the way, as the horse leans to the left here with the center of mass being this to the left here as well, there's a torque from the horse pointing to the left here, which means it's counterclockwise. And the wall, fortunately, exerts a force and therefore a torque in a clockwise direction, which balances the horse. Yet, if it wasn't for friction, then the horse would slip this way, so to the right, which means there must be friction to the left to counteract that. So the 1,430 newtons the wall exerts to the right must be compensated by a total of 1,430 newtons from the friction on both feet to the left, and again take half of that, 715 newtons, and that's what they did right here. That's the 715 newtons. Okay. Then they want to know a little more here, which is actually the total force that it said, the total force that it says in here. And hold on, I have to keep clicking forth and back here. So past the 750 newtons, that's the frictional force. And then the normal force, which is pointing upward, well, that's just half the weight. So 500 kilograms is 4,900 newtons. And again, each foot, so divide by 2, that's a 2,450 newtons. That's a normal force pointing upward. Okay, and then in this next sentence here, they do this a little bit too fast. The total force then combines the frictional force right here and the normal force right there, and they're at right angles with each other. You can see that from the drawing. Is the frictional force to the left, the normal force straight up, which means right angle, which means Pythagorean. So that means, again, I have to figure out where I am on which slide here. And that means that you do the Pythagorean 715 squared plus 2,450 squared, take the square root of that, and indeed you come up actually with 2,550. And instead of me just talking, I can show you that. So 715 squared, I said a moment ago, plus 2,450 squared parentheses, and again that's because the two forces are perpendicular to each other, and that is the 2,550 newtons that they mention here. Then they also determine the angle, and again they did that a little quick here without telling us how. So that one would be that you look at the two force vectors and you use the tangent, respectively the inverse tangent, and then you have the negative 715 divide by 2,450, and you come up with negative 16.3 degrees, just like they say right here. And the negative 16 actually would be in the fourth quadrant, but that's the way a calculator works. It only gives you one of the numbers. There's also, it's actually in the second quadrant when you look at the drawing, because the horse leans to the left. So I would add that 16 degrees to 90 degrees, so the horse is leaning at an angle of 106 degrees from the positive horizontal, which is what you can see here. So kind of like here, 106 degrees. Okay, then they want to do yet one more. Again, I have to find this here, which is the coefficient of friction. Well, this is the definition for friction. Friction equals coefficient of friction times the normal force. And the normal force equals the weight because it has to balance the weight. So it just comes out that the coefficient of friction is friction itself, which is of 1,430 newtons that I gave earlier, divide by the weight 4,900. You come up with 0.292 for that. All right, finally done with this problem. All right, the next problem, I think, is the wheel and axle. And there's a number of others here. So here's, for example, the nail puller here. That would be a lever, which I put over here. Torque equals force times lever arm and so on, typical. But then the one that I want to do is your typical car has an axle of this much, was a mechanical advantage, assuming the simplified model in this figure here. So mechanical advantage equation. This is actually quite simple, straightforward. Look, this is all it takes. Just divide one radius by another, and that gives you actually the mechanical advantage in this case of, you divide the two radii, you get 0.04, which means basically done. I'm basically done with this problem here, but I want to show a little bit more. So when I click on this one here, so here we have a number of simple machines like the pulley. Here's the crank, which actually is the wheel and the axle. And then here's the wheel and the axle that you're familiar with. This one here, I put a long note on here for myself. So there we go. On a powered, this is what I said, on a powered wheeled vehicle, the transmission exerts a force on the axle which has a smaller radius than the wheel. The mechanical advantage is therefore much less than 1 instead of larger than 1. The wheel and axle of a car are therefore actually not representative of a simple machine whose purpose is to increase the force. You're still not getting a free lunch in a simple machine, but you're able to increase the force that you actually apply. You just have to do it over a longer distance. You still have to exert, put in the same amount of work into it. The friction between the wheel and road, and here's the explanation why this mechanical advantage is so small, 0.04. The friction between the wheel and the road is actually quite low, which you know when you have a car on a on a parking lot and you put it in neutral and you just push it, and it's actually relatively easy to push, and then keep moving. So the friction is relatively low, and so that even a small force is exerted on, the axle is sufficient. There shouldn't be an is there. There's one too many is. The actual advantage lies in the large rotational speed at which the axle is rotating things to the transmission. So I pulled this one here up. This is the wheel and axle. It's a simple machine, and actually notice that the drawing they use here, that's a windlass. You exert a force on the outside, a larger radius here, and then you have a smaller radius, and you increase the force as you pull up that bucket full of water that's in there. Again, the car is actually in the other way around. You have a small radius here, which means you need a large force here, and then you get a smaller force over here. But again, you don't really have to overcome much force because the friction is relatively small. So you can afford to do that. It's kind of like, well, simple machine in reverse. All right, so the next problem I want to do is this one here with the biceps muscle, and that's also where you see us drawing here. So I'm going to go to the original problem. Oh, that's actually we need to go to the actual problem first. So we analyze the bicep muscles and so on, find the force exerted by the bicep muscle when the angle is 120 degrees and the form is in a downward position. So now I can actually go to this drawing here. So, whoops, there it is. So here, this one here in your elbow between the two bones, that's actually the pivot point right here, and depending on if you use the tricep muscle or if you use the bicep muscle, the torque acts in a different way because one of them is to the left and the other one is to the right. In this case, it's the bicep muscle biceps, sorry, that needs to exert the torque as it needs to contract in order to counteract the torque. Notice that the book produces a clockwise torque. So does the forearm, which is stretched here, also produces a clockwise torque, which means the biceps muscle must produce a counterclockwise torque. And again, the triceps actually cannot do that. It would have to stretch, which means, yeah, muscles are supposed to contract, and that's where they are exerting a force. So, and then it's basically just saying that the net torque is 0, which means you have a torque from the biceps muscle, again, positive because counterclockwise, and 2 negative torques because they're clockwise from the book as well as from the forearm. And then when you go to the problem here, this actually confused me at first. When the angle is 120 degrees and the forearm is in a downward position, which means that we would have to look at this drawing as if everything is in downward position, and then it turns out that this particular force would point to the upper right, and this one here would point to the lower left, and this one here would also point to the lower left, all at 120 degrees. And that's why they say in the problem here in the solution, the all angles are the same, so the sine functions cancel. I'd be a little bit careful with that. Yes, all angles are the same, but some of them are plus 120 and some of them are negative 120, such as this one is actually a positive 90 and this one here is actually a negative 90, which gives us the negative that we need for the weight so that we can get, in this case, a negative for the clockwise torque as well. The algebra still, oops, clicked on the wrong thing. There you go. Still clicked on the wrong thing. There it is. The algebra here still comes out to be the same here. So the net torque is all these 3 torques added here. Again, this one here actually should be on the left here. These 2 here are actually negative, again, because the angle is 270 degrees, or in this case, negative 120 degrees. So both of these are actually negative here, and then this one is a positive 120 degrees, just like they said, they divide out. And when you multiply all these numbers, and I can show that, I have to find my calculator here. There we go. So let's see, let's look at the forces that they had here. So the book's torque would be 4.0 times negative 9.8 times the lever arm, which is 0.38, and that one is a negative torque because it's clockwise, plus the one for the lever arm, which is not lever arm, I mean the forearm, 2.5 kilograms, times negative 9.8 times its lever arm, there's the lever arm, 0.16 meters. So those are the 2 torques, clockwise torques, and that would then have to be divided by the lever arm for the biceps muscle. So I divide by 0.04 and come up with a relatively large number. There it is. And to think about, why is that negative? Well, it turns out when I do the calculation, I have to get that. I have to get that to the other side, which introduces yet another negative. So I simply multiply that by a -1, which gives me the 470 newtons upwards, which makes sense because the bicep muscle is pulling it upward. All right, so what I'm going to show with this one here, I hope this works and my webcam is able to capture this here. So here's my arm, and here's my bicep muscles and my triceps, and they're both of them quite relaxed, except actually my biceps does have to hold my forearm, so it is a little bit tight. So here's the physics book that I'm supposed to carry here, and I can definitely notice when I do it this way here that the bicep muscle really is pulling on it to counteract that torque, while here the triceps is actually not doing anything. On the other hand, if I do this particular exercise here against, there's a cabinet here that I'm pressing against. The cabinet, of course, presses back at me, and now I can feel my biceps, and it's totally relaxed. It's not doing anything, but my triceps is the one that is producing the counter torque. As I push against the cabinet wants to push back on my hand, and in order to counteract that torque, so it's not being pushed out, that's where the triceps comes in. So depending on which kind of exercise you do, it's one or the other muscle that is exerting the force in order to counteract the torque. All right, so here's another seesaw problem, and this one says unreasonable result. So uniform seesaw, 3 meters long, which means negative 1.5 to the left, plus 1.5 to the right. First child has a mass of 30 kilograms, sits 1.40 meters from the pivot. They should tell us to the left or right. Let's assume it's to the left. And then you have, which is almost at the end of it actually, calculate where the second child that is actually quite a bit lighter, 18 kilograms, must sit, and we can already picture, hey, that's not going to work. This is not going to be fun for the other kid, because if that kid is anywhere on the seesaw, the heavier one being so far out will just keep the seesaw down on their side, and the other kid can't do anything. It's kind of hovering in the air there. So anyway, the way to do this is to say that the net torque ought to be 0. They kind of leave, there it is, actually a net torque right here, gravity over here, yeah, right there, weights times distance. Again, I would write it, the net torque equals 0 respectively, and net torque is 1 torque plus the other torque equals 0. That's the way I would write it. And then it's a simple ratio for these kinds of, for a number of these problems. So 30 times 1.4 equals 18 times the unknown, and yes, you do come up with 2.33, which is way off. The seesaw is not that long. So yeah, the position of the first child must be shortened. That means brought closer to the pivot. And that was, let's see, where was that one? This one here with the seesaw, and then pretty much I say the same thing here. I guess I calculated at most 90 centimeters from the pivot. All right. All right, so this is chapter 10, rotational motion, and problem 10 about the merry-go-round, and here would be the typical one. I'm just going to pull this up here, and they have already started here, and they were inside.
Okay,
so
on the count of 3, back in. Daniel, you're not out. Get out. Everybody way out. Stick your legs out even. It's going really slow. On the count of 3, go back in. 1, 2, 3, go. Now the last one in is trouble. Back.
So I just rewound this here. So it shows that depending on the moment of inertia, you either go fast or you go slow. So notice the mass is the same no matter what, but the distribution of the mass is different. So here they're all out, so large rotational inertia. In fact, he told them to even put the legs out to increase the rotational inertia, moment of inertia, and therefore decrease the angular velocity. And then they all move inside, and smaller moment of inertia means then faster angular velocity, which means there's also a torque working on these here, and that's a little bit hard to explain how they actually produce the torque here just from this particular video here. Earlier it was, of course, the father who applied a torque here at a right angle, force times lever arm produced a torque right there. There we go. All right, so going to do this problem here. I have to look at the original problem. So this problem considers, and so on and so on. How long does it take the father to give the merry-go-round an angular velocity of 1.50 radians per second? So I'm going to go to this one because the numbers are going to be in this one, and there's just a little note here on the side that says Newton's second law, sum of the torques equals moment of inertia times the angular acceleration. So this is where this one is originally coming from. Let's see, I'm going to click on this one here. And let's see, consider the father pushing a playground merry-go-round. He exerts a force of 250 newtons at the edge of the 50-kilogram merry-go-round, which has 1.5 meters radius. Calculate the angular acceleration produced when no one is on the merry-go-round as the picture shows. And then, oh, as the picture shows, there it is. I was wondering all the time here, when an 18-kilogram child sits 1.25 meters away from the center, and I'm saying right here, seriously, where's your child? Where is your child? So pay attention to that. Oh, by the way, a moment ago, you might not have seen my note. I think that was off the screen. There it is, actually. Newton's second law, sum of torques equals moment of inertia times angular acceleration. So, all right. We're only going to do part A, and then we can look at part B here as well. So I'm going to go over to, there we go. So for part A, we actually just need one of the kinematic equations for rotation. So it starts from rest, that's the omega 0, and then we have a certain acceleration, which is not given, I just noticed. So I actually need to put something in here before they do that. The equation here is correct, but as they're asking for the time, well, it starts from rest. It acquires 1.50 radians per second. That's here. But where's the alpha coming from? Where is the angular acceleration coming from? Well, that actually is Newton's second law. So I'm going to give myself a break to actually compute that. All right, so here I typed it in. Here's Newton's second law. Sum of the forces equals, sum of the torques equals moment of inertia times angular acceleration. Then the torque is also force times lever arm, so I plug that in for the torque and figure out the angular acceleration, which is, and I'm going to make this bigger here at this point. Give me a moment. There we go. Oh, it's just too small on there. Then I'm going to be off screen here. Yay. Okay. So therefore I get this one here, alpha equals force times lever arm divided by the moment of inertia. The force is the 250 newtons that were given in that example problem times the lever arm. That's where the father grabs onto it, 1.50. This is the moment of inertia for just the merry-go-round, so 50 kilograms times the radius, 1.5 squared. And then this child, which is 18 kilograms, sits at a distance of 1.25 squared. Notice that for a disk, there is the factor 1/2 in front. That comes from the table for moment of inertia. For the child, because it is just, so to say, a single mass sitting a certain distance from the axis, there's just a factor of 1 in the front. And when I plug that all in, there's already the result, but here it is. I almost have it plugged in here on the calculator. I just need the 1.25 squared here, parentheses for my denominator, and if I do it all correct, I should come up with the 4.44, and that is in rads per second squared. Now I can zoom out here again, hopefully, there we go. And then I noticed as I was typing that, just in my break here, I noticed, oh, it's already in the example here. So here they give us this. This is the 375 Newton meters in the numerator, and then here this is the moment of inertia for the just the disk of the merry-go-round is the moment of inertia for the child sitting a certain distance, and at the end they come up, well, obviously with the same number I did, the 4.44 rads per second, but I need that first in order to continue or actually start the problem here. So this is where the 4.44 rads per second squared comes from, and the other numbers are also given in the problem. Plug them in and you come up with 0.338 seconds. A little bit too accurate here. We'll just call it 0.3 seconds, but there's 3 significant figures in here, except this one here looks like a rounded number. So I'll call it 0.338 seconds. And then the rest, yeah, that's how many revolutions. So not very long, like 1/25th of a revolution, that's it. And then, or just slow it down, also not very long, 0.3 seconds. And that is this first problem here that I wanted to do, number 10. As I said, the other 2 answers were already given here anyway. And I'm going to take a break to get ready for the next problem. And the next one I want to do is about this soccer player. So I'm going to look at this one here. Let's see, there we go. A soccer player extends her lower leg in a kicking motion, exerting a force with the muscle above the, above the knee and in the front of her leg. She produces this much of an angular acceleration. Her lower leg has this much moment of inertia. What is the force exerted by the muscle if the perpendicular level arm is 1.90 meters? And my note here on the side is for this one, torque equals force times lever arm, and Newton's second law, sum of torques equals moment of inertia times the angular acceleration. So just the same as before. In fact, here it is. So here's the net force. This is Newton's second law. There is the, and that, actually this one here, net force equals moment of inertia times angular acceleration, and then the torque itself is lever arm times force. I like to use an L for that. They're using an R for radius. Again, here in the previous problem, notice that I tried to use an L here, but of course it's hard to write. I had to actually zoom in to show you that this is an L and not a 1 or something, or an I. So, all right, and then they plug in the numbers, the same numbers that I just wrote out here. So 0.75. I'm going to double check these numbers because this number here looks odd to me. I'll be back in just a moment. Okay, I double checked it, and that this number here is correct, because when I read here, so here's the moment of inertia, and they must have calculated for us already. So assume that you have the lower leg there attached to it, and then it's quite a large acceleration. But that also means, yeah, it's very quick. And there's a phone ringing, so I have to pause it. All right, took the phone call. So what is the force exerted by the muscle of its effective perpendicular level arm is 1.90 centimeters, and so that 0.019 in there is correct. And then when you plug these in here, and you can put on a calculator, 0.75 times 30 divided by 0.019 meters, that indeed comes out to 1,180 newtons, which is quite a bit. That's 250 pounds of force that goes in there in order to just move the lower leg, and then it's going to kick the ball and whatever that force is. So it's about the force that actually accelerates the leg. That's what that one is about. And if I look at this particular diagram that I have here, or the video here, we can see that. Oh, actually, I don't know exactly where that is. We would have to look at the anatomy. Oops, clicked on something different here. We would have to look at the, I keep clicking on the wrong thing here. We would have to look at the anatomy of a leg, and I don't have that in front of me. So I'm going to go to this arm that we had looked at some point. Oh, I hope I can find this. Oh, there. Here. Oh, in fact, there it is. So this here, there was the muscle here, and I think they're just talking about this short distance here to the muscle. Kind of like that. So from the pivot point of the knee to the muscle. So that is indeed 1.9 centimeter, which is like 3/4 of an inch. So that's really what they meant by this one here. Okay, again, give myself a break before I go into the next problem. All right, so the next problem is this one here, 15, about the motorcycle. So the first part is already done. Angular acceleration is this much. That's a big angular acceleration. Tangential acceleration we're going to compute in just a moment here. And then the time to accelerate is the 0.8 seconds that we see here. Here would be the original problem. So let's see. Yeah, the only note that I have here is this is about tangential acceleration. So here is the original numbers. And then with the 2,200 newtons, which is in the neighborhood of 500 pounds, so it's quite strong there in order to accelerate the motorcycle, and so on. And this is where you got this large acceleration from. And then this is actually the question here. So what is the tangential acceleration of a point on the outer edge of the tire? And all you have to do is multiply the already given angular acceleration times the radius, and that is the tangential acceleration. So that's this one here. So again, this was already computed here, and I just copied that actually, and then this one here is the way it's computed. So multiply that by the 33 centimeters, or 0.330 meters, you come up with 32.3 meters per second squared, which is 3 times gravity actually, but you know, it's an acceleration that has nothing to do with the weight or gravity. Okay, and oops, there's actually a wrong symbol. I put a wrong symbol there. That's supposed to be time, not omega. There we go. All right, that was actually it for this one. All right, and the last one I want to do is about this gymnast. So number 19 here. And how long time it takes to, let's see. Oh yeah, so she is landing. Yeah, it says here, so a gymnast is doing a forward flip, lands on the mat, and exerts a 500 Newton meter torque to slow her angular velocity to 0 so she can nicely stand. And let's see if I go back to this one here. Yeah, so that if you watch this one here, you can see these tumbling world championships. And I have not reviewed this before, so okay, is this hanging up on me right now? I'm gonna pause. All right, so I actually did have to open this in a different frame here. So this one here, I'm only going to show the first two here. So here's the Canadian, and here she has to apply enough torque for her to stop, and there she cannot. So here's the Belgian, and we can see that she is able to do it mostly right there. That's what it is. So that's in order to stop the tumbling, you have to exert enough torque on there, which is force times the lever arm. So let's look at the problem here. Gymnast doing a forward flip, lands on the mat, exerts a 500 Newton torque to slow her angular velocity. And that would be actually, the lever arm is probably between like the toes and the heels, something like that, or within the muscle itself in order to produce that. Her initial angular velocity is this much, 10 rads per second. That's almost 2 revolutions per second. They were pretty fast there, right? And her moment of inertia is this much. What time is required for her to stop exactly stop her spin? And then, yes, it does say unreasonable result. So let's go through the motions and see why that is actually unreasonable. I'm going to go back to let's see what, there's only answer A here and then answer B and C and so on. So we're only going to look at answer A, what we're going to do. So here are the numbers that are given. So the torque here, the 500 Newton meters, then the initial angular velocity, which is then being slowed down to 0, and then the moment of inertia 0.05. Again, this is Newton's second law. So the torque is moment of inertia times angular acceleration. Determine the angular acceleration of negative 10,000 rads per second squared. That's really, really big. And then go through the kinematic equation. So here, they should have written right here -0 just to indicate that. So, and then divide by that, and you come up with 1 millisecond for the time in order to stop. And I think that's actually what it's being asked for. Yeah, the time. All right. That already sounds a little bit unreasonable. 1 millisecond, 1,000 of a second seems just too fast. And I think I know where it lies. It's in the moment of inertia. This is way too small. If you imagine her as a rectangular slab in order to make it easy to see what's going on there. And if you took me and determine my moment of inertia, I would have a mass of 100 kilograms, and the length of my body would be close to 2 meters. I know I'm only 175, but I'm going to just use the 2. It's easier to calculate. So I would have 100 times 2 meters squared, which is 400. And then I have actually a factor of, I believe, 1/12 in the front for a slab that is rotating. Sorry that I call it that way. And that rotating slab, I think it has a factor of 1/12. Yes, it does. In the front, and that would be then approximately 20 or so. So 20 kilogram square meters for myself. But notice they only give us 0.05, which is way too small, which is what it says here. The moment of inertia is much too small too small by 1 or 2 orders of magnitude. The torque here is actually reasonable, but if you make this one here, for example, 100 times faster, then you come up with a stopping time of about 0.1 seconds. That seems more reasonable. All right, and those are the problems that I wanted to do on this one.